Let's learn real analysis on TikTok part 5. There's a lot to cover today, so let's get into it. A few days ago, we talked about the axioms of an ordered field. Pause to read if you want to remember what these are saying. But these 14 rules allow us to prove many interesting things about any number system that satisfies these. For instance, in the rational numbers or the real numbers, all of these theorems on the screen are true because we can prove them just using those 14 axioms I just showed you. In fact, notice some of them are pretty interesting, like that if you square any number, you always get something that's greater than or equal to 0. Now, you might hope that we could use those axioms to prove everything about number systems and just develop all of calculus. There's a big problem though. In fact, it's almost a scary problem. For instance, there's no way to prove that 2 has a square root using those axioms. And the reason for that is simply that the rational numbers themselves form an ordered field. And so if we were able to prove that any ordered field had a square root of 2, then that would mean that the square root of 2 is a fraction. And it's not. The square root of 2 is an irrational number. So clearly something is missing. But it gets even scarier than that. For instance, using those axioms, it is impossible to prove the statement I have up here, which feels like something we should be able to prove. This is basically what's called the Archimedean principle, and it says that if you have a number, if you start at 1 and 2 and 3 and 4, at some point you will get bigger than that number you started with. I think that feels pretty intuitive, but I promise you, you cannot prove it from those 14 axioms that we had before. If we keep looking, we can probably find more problems with these axioms and see how different it is from how we think the real numbers to be. But rather than get too depressing, I'm going to give you some good news, because if we add just one axiom to the list, this thing up here called the completeness axiom, then it solves all of our problems. In fact, if you look at number systems that satisfy all 15 now of the axioms, including this completeness axiom, there is only one number system in the entire universe that satisfies all of them, and it's the real numbers that you've been familiar with your entire mathematical life. Now, I would venture to say that maybe we aren't so familiar with them, since there's lots of weird things we're going to learn about in this series, but if you think about real numbers as points on a line with no gaps missing, or if you think about infinite decimal expansion, those are the real numbers we know and love, and those are going to be the things that we're studying. It's worth saying something. Now, I'm used to thinking about real numbers as decimal expansions, but you may be used to thinking about them in a different base, maybe with binary expansions. In fact, someone else might be interested in thinking about them using what are called Cauchy sequences or Dedekind cuts. You can think about these as just different ways of writing a number down. Like writing down the number 10 might look different in binary as it does in decimal, but it's still the number 1 plus 1 plus 1 plus 1. We do that the right number of times. But when we say that there's a unique, complete, ordered field, I mean up to these sort of rewriting things. If you're wondering what this completeness axiom says, it says something very intuitive, that if I have a set, and maybe it's very complicated, but I know everything in that set is smaller than 100, this axiom says I can actually refine that, maybe a little bit, and go down until I get the best or the optimum upper bound for this set. Using that, we can actually go back and prove the Archimedean principle. We can show that given any real number, there is some whole number that is going to be bigger than it, and lots of other various technical tools that we'll be using throughout this course. Next time, maybe we'll actually do a proof where we show how we could show something is the least upper bound of a set, and see how we can use the Archimedean principle to provide a precise proof.